There are a multitude of reasons why someone might want to study machine learning. It may be out of pure curiosity. For example, they just hear it all the time in the news and they kind of want to gain some insight onto what exactly it is so they have more context when reading or consuming these news media. Or they may be money driven or money hungry. They see that machine learning engineers make a lot of money and they want to hop on the bandwagon. Or it may be a part of a degree requirement that they just want to get over with so they can enter the job market and make some money. Regardless, we'll go over some notes that I have at a high level of what machine learning is. We'll talk about the classification problem and essentially a little bit about prediction theory. So, what I like to do is I like to set the scene. Um, so, in this scene, you're a bouncer at a club called Mission. If you're in the New York City metropolitan area, you would be kind of familiar with this. So essentially, this is like a hot nightclub amongst younger people, Gen Z demographic. Although anyone can go, but in order to get in, you have to pass a vibe check, right? And let's suppose you're a bouncer and you want to vibe check people as they come in, but you want your life to be easier. You want to make some passive income. You want to play on your phone, do whatever instead of check whoever comes in. So you decide to train a machine learning model to do this for you. Um, how do you go about this, right? So in general, when people write code, they tell the machine exactly what to do. If I want my code to um, be able to accept payment, then I tell the code in the logic, accept payment, take this credit card, verify it, um, you know, talk to the bank, blah blah, and make sure that transaction goes through end to end. But if I wanted to do machine learning, instead of telling the computer or machine exactly what to do, I'm telling the machine how to learn, right? And in order to learn, you need some examples, right? As a kid, we don't just learn automatically. We need to do some examples. For math, we need to do some practice problems. For reading, we need to learn some vocabulary words. So, similarly with the machine, it needs to learn how to do the task that you want it to learn. So in this case, you want it to classify whether people are cool or not to get into the club that you're a bouncer at. So in order to do that, you need to give it a lot of examples, right? For the sake of this problem, let's say either you're cool or not. There's no in between. So in order to tell the computer to learn from these examples, we need to have a lot of images, right? So because presumably you judge based on people's appearances. You're judging based a book based on its cover. So you need to give the computer a lot of images and a lot of labels with that image. So for example, if you see an image of a person, it may be labeled cool or not. And it needs to learn from a multitude of examples and that are diverse. That way, when it sees an example it hasn't seen before, it can predict pretty accurately. Um, whether the person is cool or not to come in. So, kind of as I mentioned before, machines and computers are not sentient beings, right? Humans notice a lot of nuances and are really emotional, and computers they only recognize binary bytes, zeros and ones. So we need to feed or tell the computer to be able to learn from things based on zeros and ones. So, for example, in our example, this is what's called a classification problem. We have our input features and our outcome, right? So in this case, to make it simple, we only have two outcomes. The guess is cool or not, one or zero. Features, in this case, are observable information that about said guess that we can represent in some form to the computer. That may be height, that can be represented as a number. Um, whether or not they're wearing a hat, that can be represented also as 0 or 1. So we call a one hot encoding. Other factors include like their fit, their confidence, the number of women in the group, which is really important allegedly. But for now, for the sake of this, in my notes, we only care about these three examples, and we represent features generally in a vector, and that vector can be any number of dimensions, where d is a real number or an integer, positive integer. In this case, we have 3 dimensions. We only care about 3 factors, right? So, an example of an input feature would be, you have a tough fit, you got medium confidence, you're in a group with 3 women, or something like that. You generally want to quantify these with some real numbers, as mentioned, because numbers can be represented in binary, and binary is the language which computers and machines speak in, right? So now we have, like, kind of how we want to present our data for the machine to recognize patterns. We want to kind of formalize things, right? So we want to make or define our predictor, which is what our AI is going to use. So we just have a mapping where we take in, we just call it F, you can call it whatever, where we take in X, which is our d-dimensional vector, and we output Y hat. The hat on the Y just means that it's a prediction. It's just some standard notation, cool or not in this case, 1 or 0. So the goal is we want to train from our example data, which I mentioned earlier, right? You might have like 1,000,000 images, you might have 1,000 images. I think, the more images, the better. But one thing to consider, and I don't think it's in the notes, is how much of that data do you want to learn from, right? Because if you use all of the data, all 100% of your data points to train your model, you may not have any data to, test or verify, how good your model is, right? Next part, we kind of talk about what makes a prediction good. And you ultimately need to verify with some, you leave some data points aside that you didn't learn with to as a source of truth. So when you train your model on, a good percent of the data, whether it be 80%, 90%, up to you. You want to leave 20%, 10% to use as, let the model see for the first time and see whether or not that prediction matches the true label, right? And that's kind of what I talk about in this next section. What makes a prediction good. If you let someone in uncool, so, okay, I'm getting a little ahead of myself. So there's something called a loss function, right? So what's the consequence of misclassifying? It's really dependent on what you want to achieve with your model. So in this case, it's low stakes. You let someone in that's uncool in, whatever. A few people may not have the best time, but you're still making money. You're still charging them cover at the door. In an application like cancer prediction, that could be really costly, right? What if you classify someone as not having cancer when they actually do have cancer, right? That's a really costly misclassification. So, how good you want your model to be, how costly your mistake is really application dependent. Of course, you want to strive to be as close to perfect as possible, but it's just really hard to, and most of the time not feasible. So you strive to be a good percentage, 95% or above. So formally, we can define a loss function as the cross between the two y spaces. So in this case, the y is only 2-dimensional, and we have 2 y spaces because you have one, which is the true label, one of these, and the other is a prediction. Cross those. You use the cross product, those 2 spaces, and you want to output a real number, a positive real number, right? Loss, you want to define as positive. This is much easier. So in this case, because we're only having 2 classes, we just call it 0-1 loss, right? 2 classes, 0-1. And then all mistakes are equal. You weight them equally. In other applications, you can weight them not equally. So for example, cancer, false negative is really costly. You want to weigh that way more. And this is just formally defining it. The subscript 0-1 for 0-1 loss takes in the predicted label and the true label, outputs 0. You lose nothing. There's no mistake or consequence if the labels match. You just output 1 if they don't match, right? You can use what's called an indicator function, which is a 1. Inside you take in some clause that could be either true or false. and it just returns 1 if the clause inside is true. And then putting that all together can define something called an error rate. So what percentage of the time are you making an error, right? It's simply just the average of all the mistakes. So you're just summing over all the mistakes or mismatches in classification, and you're dividing by the total number of points. Just a simple average, non-weighted. And you get, with the error rate, you can calculate the accuracy. So if your error rate is 5%, your accuracy is 95%, right? So the error rate plus the accuracy should equal to 100%. And in practice, most applications that are not, life-threatening or super consequential, you want to shoot for something around 85% or higher, in order to be considered good. Once again, though, it is application dependent. Kind of mentioned earlier, though, sometimes you have mistakes that might be more costly. So this is what we would call cost-sensitive loss. In general, this is formulated with a kind of confusion matrix where you can define the losses. Generally, when the labels do align, so when the y hat matches the y true label, you have a cost of 0, but in the other diagonal, you can define it as needed for your application. And then risk, a really small thing you want to touch on is the expected loss, right? So how risky is your model, right? If you have a higher expected loss, that means it's really risky. You're expected to have higher consequences, a higher value of consequence. So you want to minimize risk, maximize accuracy, minimize error, however you want to frame it, right? And so that's kind of a high level overview of what's called the classification problem. And I'm going to talk a little bit about one type of classifier which is really optimal. You can kind of see on the screen, which is the Bayes classifier, and we can talk a little bit about its optimality.